In this example, we've got a particle on a smooth horizontal surface, and three horizontal forces are acting on the particle as shown in the diagram. We need to find the magnitude and the bearing of the resultant force. Let's start by taking a look at some of the key words in the question. We've got a horizontal surface. In the context of this question, you can imagine that this means we're looking down on this particle from above. Perhaps the particle is on a table, and there are three forces which are trying to pull it across the table. We want to find out what direction does the particle go in and how big is the force acting on it. The general idea to solving these problems is to take all of the forces and replace them with two forces in perpendicular directions. Once you've done that, you can reduce the problem to a bit of simple trigonometry and Pythagoras to find the answer. So let's begin by resolving to the right. We've got a 200 Newton force acting to the right. To the left we have a component of the 120 Newton force. We're crossing the angle, so that will be minus 120 cos 25. We have a component of the 180 Newton force. That will be 180 cos 55. On the right hand side, rather than having mass times acceleration, we're only interested in the net force, so we're simply just going to do this calculation. And if we do that, we get minus 12.0. However, later in the question, I'm going to require the magnitude of this value. So what I'm going to do on my calculator is multiply by minus 1 and then store that value as A. Next up, I'm going to resolve up the page. The 200 Newton force can be ignored. I have a component of the 120 Newton force. That will be 120 sine 25. Down the page, I've got a component of the 180 Newton force. Again, not crossing the angle, so that will be sine as well. Putting that into our calculator gives us minus 96.7. Again, I want the magnitude of that value later, so I'm going to multiply by minus 1 and then store that as B. Next, I'm going to take these two forces and represent them using a right-angled triangle. So when we were resolving to the right, we got minus 12.0. So starting from a point, I'm going to draw a line to the left of length 12. When resolving upwards, I got minus 96.7. That means I'm going to draw a line downwards in my triangle of length 96.7. And my resultant force will be represented by a line that goes from the start to the finish. We'll label the magnitude of the force R, and we'll label this angle in here theta. So what we've done so far in this question is taken three forces and replaced them by two forces which are perpendicular to each other. This now means I can use Pythagoras and right-angled trigonometry to find the value of R and theta. To find R, we use Pythagoras. As we have the exact values stored in our calculator, we can simply do a squared plus b squared and then square root the answer. And that gives us 97.5 newtons to three significant figures. Next, we'll find the value of theta. We know the opposite and the adjacent, so we can say that tan theta equals opposite over adjacent. As we've got these values stored, to find the value of theta, we can do inverse tan of b over a. If we do that, we get 82.9. Notice that I've not rounded this answer yet because I'm trying to find the bearing. So this force is acting at an angle of 82.9 to the horizontal. As this angle is 55, it must be steeper than that, so it's going to come down here, where this angle in red is 82.9 degrees. But remember, I'm trying to find the bearing. Bearings are always measured clockwise from north. So starting from north, the angle I would like to measure goes around here. So there are different ways of getting to the answer. What I'm going to do is I'm going to use the fact that if I go 3/4 of the way round, that will be 270 degrees. But that's too far. I need to go back the distance that I've travelled for this angle here, 82.9 degrees. So in this case, my bearing will be 270 minus 82.9, which gives me 187 degrees if I round to 3 significant figures. Okay, here's a similar problem then. Pause the video, have a go, and then come back and check your solution against mine. Welcome back, here's my solution then. So first, we're going to resolve to the right. We've got a component of the 70 Newton force, that'll be 70 cos 15. We've also got a component of the 50 Newton force, that'll be 50 cos 62. And then in the other direction, we've got 60 newtons. We'll put that all into our calculator, and that gives us 31.08 and so on. As we want to use this value later, we'll store it in our calculator as A. Next, we'll resolve up the page. We've got a component of the 70 Newton force. We're not crossing the angle, so that's 70 sine 15. We've got a 50 Newton force acting down the page. We're not crossing the angle for that one, so that will be 50 sine 62. And if we put that into our calculator, we get minus 26.03. As we'll be using the magnitude of this later, we'll multiply it by minus 1, and then store it in our calculator as B. Next, we'll draw a right angled triangle to represent these two components. From our start point, we're going to go right by 31.08. We have minus 26.03, which is telling us to go down the page. And our resultant force goes from the start to the finish. We'll label the magnitude of this force R, and the angle with the horizontal, we'll call that theta. We can use Pythagoras to find the value of R. That'd be R squared is 31.08 squared plus 26.03 squared. Remember to use the exact values. We'll do A squared plus B squared, and that gives us 40.5 newtons if we round to 3 significant figures. Next, we'll find the value of theta. In the triangle, we've got the opposite and adjacent, so we can say tan theta is opposite over adjacent. So to find theta, we do inverse tan of the right hand side, which gives us 39.9. Next, we'll add this resultant force onto our original diagram. We've got an angle here of 39.9, which is less than the 62, so the force will be somewhere between the horizontal and the 50 Newton force. And our angle theta here will be from the horizontal. So if we want our answer as a bearing, starting from north, we go 90 degrees to get to this horizontal dotted line, plus the extra bit from our angle theta, 39.9, to give us the full bearing. So our bearing is 90 plus 39.9, which gives us 130 degrees if we round to 3 significant figures.